Greetings everybody. This video will hopefully explain, it's now part 2 of the Chapter 8 Lecture Notes, and it deals with one-dimensional collisions and conservation of momentum. And remember that momentum's conserved if the sum of the external forces acting on a system equals 0. And again, we don't want to, don't overthink what we talk about when we mention a system. It's simply, typically, there's one or more objects involved in these collisions, and those two objects indicate the system. Later on in this lecture, we're going to look at the ballistic pendulum example, where you shoot a bullet into a block of wood, and then the bullet gets embedded in the block, and it swings up to a certain height h. Well, the system is simply M1 is the bullet, M2 is the wooden block. That's our system, so we don't want to overthink it. And we're going to look at, remember, and so we're now looking at collisions in one dimension, and we're going to look at two types of collisions. One type is an inelastic collision, and the second type is an elastic collision. Well, what distinguishes the two? Well, an inelastic collision is one where only momentum is conserved, but not the kinetic energy. And inelastic collisions in the real world are the most common. Now, there's a special type of inelastic collision called a perfectly inelastic collision. That's where the objects stick together after the collision. But you can have an inelastic collision where they don't stick together. But perfectly inelastic is when the objects stick together. For example, when we do example 1, two cars collide, and somehow their bumpers lock. And so that constitutes a perfectly inelastic collision. Now, an elastic collision is one where momentum and kinetic energy are conserved. Though those tend to be somewhat more rare than inelastic, but that's the two. So inelastic collision, momentum's conserved but not the kinetic energy. Perfectly inelastic, the objects stick together after the collision. Elastic collision, the momentum and kinetic energy are conserved. Well, let's take a minute. Let's do inelastic first. So here, look at example 1. You have an 1,800 kilogram car, and it's stopped at a traffic light. Okay, and then that car is struck from the rear by a 900 kilogram car. Then after the collision, the two cars become entangled, i.e. perfectly inelastic collision, and they move along in the same direction as that of the originally moving car, meaning it's a one-dimensional collision. Then if the smaller car, i.e. the 900 kilogram car, that's the one that rear ends the car that's at the traffic light. So if the smaller car was moving at 20 meters per second before the collision, what is the velocity of the entangled cars after the collision? And ignore friction, meaning there are no external forces, so we know momentum's conserved, right? Because we're ignoring friction, we know that condition holds. All right, well, so let's apply conservation of momentum. Well, let's let M1 equal the 1,800 kilogram car that stopped at the traffic light. Okay, so M1 is 1,800 kilograms. V1 initial, meaning the speed of M1 before the collision, V1 initial. Don't let the subscripts, they can be a little bit cumbersome. Don't let the subscripts confuse you. So M1 is the 1,800 kilogram car. It stopped at this traffic light, so its initial speed is 0. So V1 initial 0. M2 is the 900 kilogram car, and V2 initial, the speed of M2 before the collision, well, it's 20 meters per second. So M2 is equal to 900 kilograms, V2 initial is equal to 20 meters per second. Now it's a perfectly inelastic collision because the two cars become entangled. So that's essentially, we're telling you they stick together after the collision. All right, well, let's apply conservation of momentum. P initial equals P final. That's the momentum of the system. And when we say initial and final, P initial is the momentum of each object, in the system. In this case, our system is M1 and M2. So P initial, that's the initial momentum of each object, before the collision. P final is the momentum of each object after the collision. Well, the initial momentum of m1 is 0 because it's not moving before the collision. The initial momentum of m2 is m2 v2 initial. Remember, momentum in general, P is equal to mv. So m1 has no initial momentum, obviously, because it's not moving before the collision. The initial momentum of m2 is m2 v2 initial. Now remember, it's a perfectly inelastic collision. The cars stick together after the collision. So after the collision, we treat them as one object with a total mass of m1 plus m2. And then so the final momentum is parentheses m1 plus m2 times v final. And that's what we want. We want v final. We want to know what is the velocity of the entangled cars after the collision, meaning we want v final. So you have pi equals pf, m2 v2i equals parentheses m1 plus m2 v final. Basic algebra, solve for v final. You get v final equals m2 v2i over m1 plus m2. Plug in the numbers. Remember, everything's given. m1 v1 initial 0, m2 v2 initial. Plug in the numbers, and you get v final is equal to 6.67 meters per second. And then here's a what if problem. Just essentially redo this problem. What if only redo the problem? What if the 900 kilogram car was parked at the light and it was rear-ended by the 1800 kilogram car? It's try that on your own. It shouldn't be too difficult. But obviously the speed won't be the same. It'd be interesting to see what you get. All right, let's look at another perfectly inelastic collision. Let's look at a very common example called the ballistic pendulum, which gets its name because from the field of ballistics. And the standard ballistic pendulum, and this is an actual photo of the lab apparatus. Here you have a pendulum, suspended from a point, and the spring gun fires a small metal sphere, and the sphere hits the pendulum. There's a little locking mechanism that keeps the sphere from coming out of the pendulum, and when the metal sphere hits the pendulum swings up to some maximum height h. And typically the apparatus is set up such that there's a way to measure the height to which the pendulum swings. And so, but here's a sketch. Here it is here you have this block of wood suspended, from a support. That's your pendulum. It's initially at rest. The block of wood we'll call M2. You fire a bullet into this block of wood. We'll call the bullet M1, and it has some initial speed. What happens is, in stage 1, you fire the bullet into the stationary block of wood. It's just hanging there. The block of wood is the pendulum. When the bullet hits the block of wood, it becomes embedded, and then they move off with some final speed. They call it VB in the sketch. We call it VF, but they move off with some immediately after the collision. The block and the bullet, it's a perfectly inelastic collision. They immediately after they move off with some final speed VB, and then the pendulum will swing to some max height h, and we know that at that maximum height h, it's not moving. The speed at the max height is 0, and so you have stage 1, stage 2, and stage 3. Stage 1, you fire the bullet, mass m1, initial speed v1 initial. Stage 2, the bullet undergoes the bullet and the block of wood undergo a perfectly inelastic collision. That's stage 2. They begin to swing together with some speed vf, and then stage 3, when the pendulum has reached its maximum height h, at stage 3 it's not moving. Well, the way you approach the ballistic pendulum is you apply conservation of momentum from stage 1 to stage 2, because the block and the bullet and the block undergo a perfectly inelastic collision. So from stage 1 to stage 2, it's conservation of momentum. Then from stage 2 to stage 3, it's conservation of energy. So again, conservation of momentum from stage 1 to stage 2, that's a perfectly inelastic collision. Then conservation of energy from stage 2 to stage 3. Okay, well let's do conservation of momentum. Well, the initial momentum of the bullet is m1, we'll call it m1v1. Remember, initially in the ballistic pendulum, the block of wood, it's just hanging there. Again, it's not moving. Right here, see? The pendulum is not moving. So the initial momentum is m1v1. The final momentum, remember, it's a perfectly inelastic collision. So it means that you have to, it's a perfectly inelastic collision. So the final momentum is you treat them as one object with a total mass of m1 plus m2. So it's m1 v1 equals m1 plus m2 v final. We'll call that equation 1. Now let's look at stage 2 to stage 3. We want to do conservation of energy. Well, in stage 2, the energy is all kinetic because you have the bullet is now embedded into the block of wood. So their total mass is m1 plus m2, and they move immediately after the collision. They move off with some speed vf. Then the pendulum swings up to that max height h. At that maximum height h, we know the speed is 0. So now conservation of energy. So the initial kinetic energy, that's at stage 2. The energy is all kinetic. That's equal to the final potential energy. The energy at stage 3 is all potential. Well, the kinetic energy, so we have KEI equals PEF. Remember, that's stage 2 to stage 3. So the kinetic energy is 1/2 m1 plus m2 v final squared. And that's the kinetic energy at stage 2. At stage 3, the PE final, the final potential energy is just, again, m1 plus m2 GH. So we have two equations, and right now we have two unknowns. And actually, let me go back. What we're looking for is we want the initial speed of the bullet. You know, that's the idea. What is this? And that's the goal. You want the initial speed of the bullet. So we have these two equations 1 and equations 2. And we have two unknowns. We don't know V final, and we're looking for V1. So let's use equation 2 and solve equation 2 for V final. Nothing complicated. V final is equal to root 2GH. Then take that expression for V final and plug it into equation 1. And then solve for V1. And so what we do is we take this expression for V final and we put it into right there in equation 1, and then solve for V1. And you get V1 is equal to M1 plus M2 over M1 then times root 2GH. And so the idea is if you know the two masses, which of course you can get M1 and M2 by weighing them, and if you know the height, then you can get V1, the initial speed of the bullet, right before it hits the block. And again, the ballistic pendulum apparatus, this is again a picture of a common one. Typically, there's a way that the apparatus is set up so there's a way for you to measure H. And then you can obviously weigh the pendulum, you can weigh the metal sphere, so you can get your M1 and your M2, you can get H, and then you know V1. So I'll go ahead and this again, ballistic pendulum, very common example of a one-dimensional perfectly inelastic collision. And again, I'll end with this. The key is its conservation of momentum from stage 1 to stage 2. That's where this equation comes from, equation 1. And then it's conservation of energy from stage 2 to stage 3. And that's how I got equation 2. And then your unknowns are VF and V1. Well, we want V1. We want the initial speed of the bullet just before it enters the block. So you solve equation 2 for VF. That expression you get, put that into equation 1, and then solve for V1. And there you go. Let me go ahead and save this video and get it posted.